Gresham College presents Clusters of Galaxies by Professor Carolin Crawford, Gresham Professor of Astronomy.
So, good afternoon everyone. Delighted to see so many of you again. So, you're back for your next dose of astronomy, and today we're going to be looking on things on quite a grand scale. We're going to be discussing clusters of galaxies. And you have to realise that a lot of the galaxies in the universe don't live in sort of wonderful isolation. They tend to be tethered together by their mutual gravity into collections such as group or giant clusters of galaxies. And that's going to be the topic of my talk today. And here's a beautiful example of one of the rich clusters of galaxies in the nearby universe. And I'm going to talk about the kind of galaxies that are inside clusters, also about the properties of the clusters as themselves, and also just the way that they're distributed around the sky, and what they can tell us about the kind of contents of the universe, and in particular about dark matter. But just to step back and talk about this whole idea of galaxies grouping together under gravity. So, for example, here is the whole sky. It's a survey of the sky, so you've got the sky and it's been unwrapped and laid flat, and every spot on here is the position of a fairly nearby galaxy. This is taken in infrared light, and each of these spots marks a source that's kind of extended, so you don't get stars, you don't get anything point-like, you just get extended galaxies in the near infrared. And altogether there are 1.6 million galaxies in the nearby universe marked on this plot. The blue band across, or the sort of sash across the middle, marks the position of our galaxy. It's kind of in the way when you're doing extragalactic astronomy. You can't see behind it very well because all the dust and gas clouds in it. And so that's obscuring some of the counts of galaxies, and it's that blue line's just to give you an idea of where our galaxy is. But as you look at this picture, one thing is quite apparent, which is that galaxies are not randomly distributed across the sky. You can see that they're all knotted together into little groups and concentrations throughout the sky. And these are the clusters. So it's showing you that they're already, even at this very simple level, beginning to cluster together. Now, 3 of these galaxies you can see with the unaided eye. So, for example, for those of us in the northern hemisphere, we might be used to seeing the Andromeda galaxy in our autumn skies. Now, this is a sister galaxy to our own Milky Way. It's a similar size, a similar mass, similar size, black hole in the middle. It's to all extents and purposes, we could be looking back to our own galaxy. This is 2.5 million light years away from us. And what you may notice about it, and you can't see these so much with the unaided eye, but it's got 2 little galaxies very clearly in orbit around it. Not sort of fluffy spirals, but little sort of ball-shaped galaxies. The same is true about our galaxies. We have dwarf galaxies in orbit around us. And if you're ever lucky enough to go and see the southern hemisphere skies, you may have seen, or may yet see, the Magellanic Clouds. And they really look for all the way like little clouds in the sky. Here you've got our own galaxy, the centre's down there, a sort of edge-on band of our galaxy crossing the sky, a gratuitous pretty comet down here at the bottom. I know it's supposed to be clusters of galaxies. I can never resist a comet if there is one to show. And here you've got 2 Magellanic Clouds. This one, the Large Magellanic Cloud, is about 170,000 light years away. This one's slightly further at about 200,000 light years away. And they orbit our galaxy. And those are the most obvious ones. There are others that are nearer or more distorted, so they're more kind of spread out around the sky. And altogether, between our Milky Way and its satellite dwarfs, and the Andromeda and their satellite dwarfs, and then also this giant spiral, well, it's slightly smaller than Andromeda in the Milky Way. This is the Triangulum galaxy. It's about 3 million light years away. So we're all kind of round each other. And together we form something called the local group. You have a group of about 30 galaxies. You've got 3 big spirals and then all their satellites. And we're all joined together. We feel each other's mutual gravity. And if we could fly outside and look back at us, we'd probably look something like this. This obviously is another compact group of galaxies. They're all over the sky. Groupings of, tens of galaxies, all contained within a volume of perhaps a few million light years across. And some of these are very beautiful systems that you see, and a complete mix of different types of galaxies altogether. Now, this is the thin end of the wedge. This isn't really the kind of system I'm talking about today, because this is only the very smallest scale. Clustering of galaxies grows and extends to much larger scales. So, for example, we have something like the Coma cluster of galaxies here. Now, obviously, some of these are stars. You can see the stars. But I hope you can see two giant elliptical galaxies here. And then it may not be so apparent from the back of the lecture theatre, but there's a whole host of other little fuzzy orange blobs, and each of those is a galaxy. Altogether, you've got probably about 3,000 galaxies contained in a volume space about 20 million light years across. The main thing to notice about, to begin with, is that these galaxies right at the core of the cluster here are truly enormous. They would dwarf our Milky Way. It's difficult to pick out a scale, but for example, you might be able to see a small kind of spiral-shaped galaxy about there. That's probably about the size of our Milky Way in comparison to these giant objects in the centre. And this is an example of a very rich cluster. Our nearest rich cluster, about 250 million light years away, is the Perseus cluster. It's one that I particularly study and am interested in. And you can see this has a different kind of shape, where there's a long chain of orange-looking galaxies, and the central, very sort of massive, dominant galaxy is over here. And you get a range of shapes, the distribution of the galaxies, you get a range of types of galaxies, and the thing that characterises clusters is basically how packly dense they are. When I'm talking about a group of galaxies, I'm saying you've got tens of galaxies within a few million light years. Clusters only perhaps occupy maybe tens, a slightly bigger volume, but you get many, many more galaxies within that volume. And we tend to characterise a cluster, we call it whether it's rich or poor. So if it's very sparsely populated, it's a poor group or a poor cluster. And going up to these kind of systems that we call a very rich cluster. And you get the full span of clustering from tens to hundreds to, as you can see, absolutely thousands of galaxies contained within this space and within this volume. Now, clusters were detected fairly early on. So as soon as serious astronomy started to be done by telescopes, for example, Charles Messier, the French astronomer, who was cataloguing little fuzzy blobs in the sky, things that he kept stumbling across. He was looking for comets, and these would confuse the issue. So he started to draw up a list of where these little fuzzy blobs were in the sky, so that he didn't just keep rediscovering them. And this has now become the very famous Messier catalogue of nearby galaxies and nebulae. But at that point, he just saw there were little fuzzy blobs in the sky, didn't really know what they were. But even he was surprised to find that there are 11 of these nebulae all within the constellation of Virgo. And William Herschel, just shortly afterwards, the same result, started to notice this concentration of these fuzzy blobs in the sky in the constellation of Virgo. Now, this is, in fact, our nearest cluster, or in fact, it's a supercluster. It's known as the Virgo group of galaxies. And again, you've got one giant system down here. And then others began to be studied, so like the Coma cluster and the Perseus cluster I just showed you. They were both studied by the German astronomer Max Wolf. And all of this was happening before we even really knew that these fuzzy blobs were galaxies outside our own. That didn't change to the 1920s, when Hubble showed that a lot of these nebulae, especially the spiral-shaped one, were other island universes, other galaxies. And at that point, you began to recognise that some of these were clustered. And it was only in the 1920s that Harlow Shapley, an American astronomer, discovered our nearest supercluster, one of the most fantastic superclusters I'm going to be showing you later. So you can see the scale of clustering doesn't just end with groups to clusters. You also get superclusters, or clusters of galaxies. And the one was discovered back in the 1920s. Serious study or cataloguing of clusters of galaxies, though, had to wait quite a while. Had to wait probably till about the 1950s. And pioneers in this respect were George Abel and Fritz Zwicky. And what you have to realise is that when you're discovering a cluster of galaxies, it's one thing to think, yeah, there's kind of a lot of galaxies over there. It's another thing to quantify that grouping. And you have to remember the 1950s, this work is done either through you're detecting stuff with eye through a telescope or through photographic plates or spectra. And so the method of determining whether a galaxy is there is all done by poring over photographic plates. And you have to realise this is quite back-breaking work. So here, for example, is the coma cluster on one of these photographic plates. And it's fairly obvious. So the first thing, for every little speck on the photographic plate that you're looking at through the microscope or it's a magnifying glass, you have to realise, is it a star, is it a galaxy? Does it look kind of slightly spatially extended? And then maybe you have to guess its distance from its size or its brightness. And then you have to look for overdensities, so groups of galaxies that appear to be all kind of together on the plate. And there's a kind of a background level of galaxies all the while, so you're looking for overdensities over what you'd expect normally. And all of this is done by sort of counting out by eye across the plate. Very subjective, because not only do you make a decision about whether it's a star or a galaxy, you need to make a decision about, do you think this galaxy belongs to this grouping? You get problems that, there may be interlopers along the line of sight that could get confused or included in the cluster. It starts to get very complicated. How big is the cluster? You have to guess how far away it is from the brightness and the size of that giant galaxy in the centre, and then guess how far out you need to count to incorporate galaxies within the cluster. So you have to repeat the counts on different days. And so this is quite a mammoth undertaking. It may look obvious for something like the coma cluster that's nearby. By the time you get to the Perseus cluster, this is actually quite low down, and you're seeing it through the kind of fringes of our galaxies, so you've got lots of stars in the way. As soon as you start getting further away, so more distant clusters of galaxies, the problem becomes a lot harder. First of all, most of the galaxies in the cluster are faint, and the further away they are, the fainter they are. You don't necessarily pick them up on your photograph. The cluster is smaller on the sky, so you're only getting the brightest galaxies, and it's smaller in the sky, and you've got more interlopers along the line of sight. So these clustered catalogues will only really survey the comparatively nearby universe compared to what we use now. But nonetheless, Abel, for example, Abel catalogue is the one that we use. He discovered over 2,700 clusters, just again by eye from examining photographic plates. And indeed, many of the clusters the really rich, big clusters that we use and we all study today, all tend to be known by their Abel number. So like Perseus here is Abel 426, the coma cluster is Abel 1656. They've all got, catalogue numbers from this Abel catalogue. Of course, today, it's much easier to find clusters. You can detect the light with CCD cameras and get computers to evaluate relative brightnesses of galaxies to actually detect them and decide whether they're spatially extended. You can use spectra, you can use colours to decide whether galaxies are real physical associations. And you'll see later we can also use information from other wavebands. Other astronomy's come on since the 1950s. We can use other wavebands and other characteristics of clusters in, say, the X-ray waveband to detect clusters at progressively more distant, progressive distances away from us. But the key thing about these catalogues is they started to have enough clusters that we could begin to compare one cluster with another in terms of its brightness, in terms of the properties of the central cluster galaxy, in terms of the number of galaxies within it and what was happening to the galaxies within it. And so that's your first, a key point where we start to understand some of the processes going on within clusters of galaxies. So here is a beautiful, rich cluster, Abel 1689. And if you look at the galaxies in that cluster, one thing that really should leap out at you is that there are very few blue fluffy spirals. Most of the galaxies, in fact nearly all the galaxies in the cluster, are giant ellipticals. They're yellow in colour because they're made of old stars. They don't have lots of current massive star formation. And in fact, anywhere where you might see something that looks slightly bluer, perhaps there's something here, a sort of foreground spiral. Here's a beautiful example. I'm willing to bet that just lies along the side. It's not actually part of the cluster. And so this is very different from the distribution of galaxies out of clusters, what we call the field. There you've got sort of, about 30% of them are spirals. In the centre of a cluster, nearly everything is an elliptical galaxy. And the more massive and the richer the cluster, the more the tendency is for all the galaxies, especially through the core, to be elliptical in shape. Something happens to galaxies in a cluster that perhaps means that spiral galaxies, if they were there to begin with, don't actually survive. And indeed, we think there are processes going on within a cluster that can transform a nice, fluffy, a very active star formation spiral galaxy to something that's what we call anemic. Perhaps there's an echo of a disk structure, but it's much more like those ball-shaped galaxies. It's no longer blue. There's no longer lots of active star formation going off. It's lost its spiral arms. And when you study individual galaxies within a cluster, anything that's slightly disk-shaped and look like it could be related to a spiral galaxy, you find it no longer has, obviously it doesn't have the blue colours, doesn't have much active star formation. It's also lost a lot of the gas. A spiral galaxy like this has a large disk of neutral atomic hydrogen, or things like cold molecular gas, all associated beyond the disk and with the spiral arms. If you look at galaxies or spiral disk-shaped galaxies that are within a cluster, they've lost all that. They're depleted in this gas. And as it's that gas that stars form from, the fact that somehow this gas has been removed from the galaxy means that active star formation is shut down, and you're left with more or less the core of the galaxy, which is this kind of bulge component. And there are a couple of processes that produce what we call this stripping. Basically, you're stripping the spiral galaxy from all that vulnerable outer edge stuff. And this happens if you have a spiral galaxy that falls into the cluster. So you have a giant gravitational mass, which is the cluster, little spiral galaxy in the outskirts, begins to fall, comes through an orbit right through the core of the cluster. And what happens is it tends to get ripped to shreds. Sorry, I shouldn't look so happy when I say that. It's very sad for the spiral galaxy. There are a couple of processes that combine together to rip it apart. The first thing, it's got lots of tidal gravitational shears and forces pulling on it. It's feeling the gravity of the whole cluster, not just individual other galaxies, but the combined effect of this. And this sort of tears and tugs at the outer layers. And here's just, for example, a simulation of starting off with a little spiral galaxy and what we reckon happens to it as it falls through. And after about maybe about a few gigayear, maybe about a gigayear, you find that all the outer extremities have got pulled off to leave behind something that's like these very anemic disk-shaped galaxies that we find in these clusters. So that's one process. We call it tidal harassment, because basically you're just kind of pulling out this little spiral galaxy, shredding off its outer layers. This is one process, but perhaps the dominant one is not just due to the gravity of the galaxies, but it's because you don't just have the galaxies in a cluster. Now, I alluded to this last time when I talked about, or the time before last, Sounds of the Universe. When you look at a cluster of galaxies, again, back to this one, you're only seeing the tip of the iceberg of what's there. In between all the galaxies and the clusters, there's a very hot gas, and it's at temperatures of millions of degrees. At those temperatures, it doesn't give off optical light, it gives off X-ray light. So if I look at this same cluster with an X-ray telescope, I no longer see individual galaxies. They're all too cold to produce X-ray light. Instead, I see something called the intercluster medium. It's just coded purple here in this picture. And it's just like a giant puddle of hot plasma that pervades the cluster. It fills all the space between the galaxies. There's probably about 7 to 10 times the mass in gas as there is galaxies. And just to superpose the optical and the X-rays together, you can see how it just fills all the space. So this is a huge hot atmosphere. You can imagine what happens if you throw a little spiral galaxy into it. It's sort of getting, we call this ram pressure stripping. It's falling through a medium. And, it can fall, say, millions of kilometres an hour through into the cluster. And this atmosphere pushes back on the outside of the galaxy and sort of pushes out and again attacks those vulnerable outer side of the spiral galaxy. Now, we do, in some cases, see this process occurring. Obviously, the richer, the more massive the cluster, the more X-ray gas is in there, and perhaps the hotter it is, and the harsher the environment that the spiral galaxy is falling into. So if we go back to the... this is Able 2667. Again, giant galaxy here. What you may notice is a little fluffy spiral out here. And that's probably along our line of sight. Remember, this is a picture of what's really a 3D situation, so it's probably somewhere between you and me, and it's just kind of falling into the cluster like this. Here, we're just getting a snapshot of this thing being torn to shreds. If I blow it up here, you can see that it's beginning to lose those knots of star formation. You get the sense of stuff streaming off the galaxy almost like a comet and getting left behind. And these little knots of star formation will just kind of live out their lives and then die away. And all this matter is being pulled off this galaxy as it starts to fall into a cluster. If we go back to the Virgo cluster, if I just look at this little galaxy here, this is a disk spiral, again, falling in at maybe about 10 million kilometres an hour into the cluster and into that intercluster medium. If I zoom in on that, I hope you get the sense of stuff kind of boiling and getting left behind. The galaxy's moving through the cluster in this direction, and you have these dusty wisps and matter being pulled up and stars being pulled up. There's another spiral example in the Virgo cluster, and again you get the sense of it's moving this way and stuff is being stripped off and left behind. And so this process, over perhaps several hundreds of millions of years, transmutes a nice fluffy spiral into something that's much more ball-shaped, much more elliptical, much more anemic. And this process has gone on, is going on, and it's part of the reason why we think that a lot of the galaxies in the centre of the cluster are not spirals. A lot of them are genuine ellipticals. Ellipticals tend to be more massive. They tend to sink more easily down to the centre of the cluster, in the centre of the gravitational potential. And in particular, I'll just remind you that right at the core of the cluster, and in terms of where that X-ray gas was, right at the centre of the X-ray gas, there is a giant elliptical. This is M87, this is the giant galaxy, the dominant galaxy of the Virgo cluster, with an enormous mass of stars. And sometimes these galaxies can have a very diffuse halo spreading much further out from the body of the galaxy. And these are in a fabulous position. They sit right at the centre of the cluster, at the centre of the gravitational potential well. They can just accrete any matter, any of these stars, any of the stuff that's being stripped off all the galaxies eventually might settle towards the core. And it receives a lot of this matter. It also has lots of other processes going on within the cluster. And so at the centre of these clusters, you get the most massive galaxies anywhere in the universe. You do not find these in the field. You only find them sitting squat in the centre of the gravitational potential of the clusters. And these are the biggest galaxies, the most massive, and they have the most massive supermassive black holes at their core. So these are some of the most exciting galaxies in the universe from my very biased viewpoint, because I study them. And just to go back, of course, you can see that the X-rays give you a fabulous way of detecting more distant clusters of galaxies. You're no longer having to count individual galaxies and decide whether they're members of a cluster or whether they're really associated with each other. Instead, you just go and look for a big puddle of X-ray gas. And so here, for example, from one of my colleagues, are some X-ray images of clusters, a relatively nearby one, and then some that have been discovered through the X-ray emission at progressively further distances away from us. You can immediately tell from the amount of X-ray light how massive the cluster is, how big it is. You can tell how rich it is. So it's a very empowering way to find very distant structures. And in particular, this is how the most distant clusters of galaxies are found. This is one where, confusingly, X-ray is now colour-coded blue, and the white are the stars. From the optical, you would struggle to see, even without that blue murk in the way, that there's a cluster of galaxies there. But this X-ray light reveals that there's the intercluster gas, showing that there's a massive amount of gravity there, pulling the gas in, keeping it hot. And that's, in fact, 10.2 billion light years away. This is about as early as we think you can actually build clusters of galaxies in the early universe. And, yesterday I would have told you this was the most distant cluster of galaxies known about. I've just got news this morning that one's been discovered at 10.5 billion light years away. So it's very competitive. So you get clusters of galaxies dimensionally throughout the universe. So there's something very interesting about clusters. The galaxies, you have to realise, are not stationary. They are feeling each other's gravity, they're moving around each other. And I just want to be quite clear about, we all know galaxies are moving apart and the universe is expanding. Yes, that's happening, but only on the very biggest scales. You have to think of groups or clusters of galaxies as isolated exceptions to that general expansion of the universe. So within a cluster, the gravity dominates. On the scale of a cluster or a group of galaxies, the gravity or the galaxies feel to each other dominate and dominates their motions. So they tend to respond to that. And so you have a pocket of what we call local motions, of galaxies going around each other. The whole cluster will be receding away from us, but within that cluster, on top of that recessional velocity, you've got local motion. So you have little pockets of motion. Now, if you study how the galaxies in a cluster are moving around each other, once you've taken out that recessional velocity, you find something very, very curious. Now, in the same way that when the Earth moves around the Sun, how fast it moves depends on how much mass there is in the Sun and how far away we are from it. For any one galaxy in a cluster, how fast it's moving through the cluster, what orbits it's on through the cluster, depends on the combined mass of all the other galaxies in the cluster. And if you sum all the motions, you can work out what mass they're responding to, how much gravity is there. If you do this, even say the Coma cluster here, you have a problem. Measure how fast all the galaxies are moving, and you find they're moving too fast. Okay? They shouldn't stay as a dynamically gravitationally bound system. They should have all flown off into space. They're going so fast that gravity shouldn't bother them. They should have dispersed giga years ago. The fact that they're all still within one coherent, stable system tells us there's actually more gravity there than we realise. There must be more gravitational attraction to keep them bound to the cluster. That means there's more mass there than you realise. And the problem is that if you work out the gravity they're responding to and you count up all the stars and all the galaxies in the cluster, you find there's nowhere near enough mass. And the discrepancy is huge. In clusters of galaxies, it can be up to like a factor of 100 or more. That means there's a large amount of mass within a cluster that is very, very dim. And it's well over sort of 100, 300, 500 times dimmer than the Sun is. And there's more mass in a cluster than we can actually see. And this was discovered, again, back in the 1930s by the wonderful Fritz Zwicky, looking at the Coma cluster. He was the first one to raise this idea that there was missing mass. I mean, obviously now we know it's not the mass that's missing, it's just the light from the mass that's missing. But the idea of what we now call dark matter. In my rotation talk, my last lecture, I talked about how the stars in a galaxy move too fast to stay bound to the galaxies, therefore we think there's dark matter on the scale of a galaxy. This is even more dark matter required on the scale of a cluster. And the discovery of this predates anything done with the rotation curves of spiral galaxies. So what you see is only the tip of the iceberg of what's actually there. Now, you might say, you've just shown us there's all this X-ray gas. You've told us that there's lots of X-ray gas there. And that's true. And the X-ray gas is much easier to map and extends out further than the galaxies. So here's a garish false colour image of the Coma cluster. So this is this cluster I've just shown you here in X-ray light with the German Rosat satellite. And it goes from purple is kind of the background level, and it goes right up to red, which is the peak of the strongest X-ray emission, where the gas is densest and most concentrated. Just to give you a scale, almost like within that central contour, you could fit those giant galaxies. Okay, so this is all this gas. Most of it is primordial and left over from when the cluster formed. Some of it's been reprocessed through the galaxies. And if you count up and include all the mass in the gas, you find, yes, there's probably about 10 times, 5 to 10 times more matter in the gas than there is in the actual visible galaxies. That's still not enough. So it's still, even if you count up the light in all the wave bands, you find there's not enough emitting matter to account for all the gravitational mass of the cluster. Key thing to remember is the X-ray gas actually is the dominant emitter. This traces most of the emitting or the light emitting matter within a cluster, but it's still nowhere near enough. So when Zwicky, announced this idea of dark matter missing mass, you can imagine it wasn't very well accepted. And in fact, it took several decades throughout the 20th century for this whole idea of dark matter to be reinforced by spiral rotation curves and other measurements of other galaxies. It's a big step. If you're used to looking at optical images, and of course our sense of astronomy grows up with optical astronomy because that's attuned to our own eyes, to realise that there's a whole lot more stuff out there that doesn't actually necessarily even bother with light. And so this idea was challenged, and if you have a really big idea that there's a huge amount of the mass you're missing, you need to reinforce that interpretation with other ways. You need to go out other ways to prove it's there. And this has been done. So obviously with other clusters of galaxies, looking at the motions of the galaxies within the cluster, that all supports it. Similarly, you can use the X-ray gas to show that there's a huge mass. All of this gas is held in place by gravity, this big puddle of gas. It's responding to the gravity of the whole system in the same way the galaxies are moving around, and that makes it hot. So if you have your puddle of X-ray gas, you can directly measure from X-ray measurements the temperature, the density of the gas that's producing this light. If you've got density and temperature, you can work out the pressure. So this gas is under pressure, and that pressure is caused by all the outer layers of gas squeezing on it, pushing in. They're being pulled in by gravity, and how much the outer layers are being pulled in depends on how much mass is there, how much gravity is there. And so from X-ray observations, you can do an analysis where you look at the way the pressure changes across a cluster, how much gravity that implies is in the cluster, and you find excellent agreement with the estimates from the motions of the galaxies. You need lots more mass than you actually see. And even that isn't quite enough proof for some people. Something that happened on the same timescale as understanding the cluster emission in X-rays is this idea of gravitational lensing. And this is the third method you could use to weigh a cluster of galaxies. And what I want to stress is all of these different methods are employing different observational techniques, different assumptions about physics involved in a cluster. And gravitational lensing appeals to Einstein's idea of the gravity not as, Newton's invisible force acting over a distance, but if you plonk a mass in space, it bends and distorts the space around it. It curves it. So, for example, not to scale, obviously, we're here. This is a very distant source in the sky, and so there's a big galaxy in between us and the source. Now, if space is all curved around this galaxy, any light that goes past it gets bent. The light thinks it's travelling in a straight line. Unfortunately for the light, the space is curved, so it ends up following a curved path. And this creates mirages and illusions of where the light comes from. So in the absence of this galaxy, the light from this background source would sort of carry on and miss the Earth. Because you've got the galaxy and the curved space around it, it gets distorted and deflected towards us. Now, as far as we're concerned, we see light from that direction, and so we see two mirages. And of course, this is a two-dimensional representation of a three-dimensional situation. You also have light that's bent this way as well as that way. And if you get a perfect alignment of source, galaxy, observer, you can get perfect rings around the mass. So here, for example, are some beautiful cases where you've got a giant galaxy and the blue ring around it is the light from the background source distorted into this mirage, this ring around the galaxy. So the key thing here is the closer you are to the mass, the more space is distorted. The bigger the mass, the more space is distorted. So you can begin to see, if you just know about the optics of this phenomenon, you can use these distortions, these mirages, to work out how much mass is there. Now, these are just examples when you have individual galaxies. As soon as you have a whole cluster of galaxies, it's quite technically complicated, but the dividends of actually mapping out the distribution of the mass within the cluster are great. And again, it was Fritz Zwicky who was the first one to come up with this idea. Einstein came up with the idea of bent space around a mass, but he only really applied it to kind of point-like masses like stars. You may not think of a star as a point-like mass, but compared to these things it is. It was Zwicky that came up with the idea that perhaps you could, the mass in clusters would be so great that you would get much different lensing distortions. However, it wasn't until the 1980s, when you start getting CCD detectors and the next generation of large telescopes, that people began to see the kind of distortions predicted to be in clusters of galaxies. Now, you may have noticed some of them in some of the pictures I've already shown you. So, oh, sorry, got to go back and explain some physics. Just keep you in suspense a bit longer before I show some mirages. What you have to realise is that mass in a cluster, or even in a galaxy, it's all kind of clumpy. It's got a bit of a lumpy distribution, especially if you've got lots of different galaxies. I used to think the name gravitational lensing is misleading because we're used to lenses that bring light to a perfect focus that suits us. When you've got a lumpy, uneven lens, it doesn't bring the light to a clear focus. It doesn't necessarily bring light to a focus near us. It may be in front of us, it might be behind us. What we get instead is something called caustics, where you get bands or envelopes where the light gets more concentrated and darker. And here are just some examples of caustics we see in every day, where light is refracted through the surface of water, say in a swimming pool or a lake, or even in your coffee cup. If you've got a clean coffee cup and you've got bright light coming down, I'm sure you will recognise this shape. That's a caustic. And again, it's the light being reflected not to a perfect focus. So the same is true with these clusters of galaxies. Now, there's no cluster here. This is a backdrop. This is the wallpaper of the universe. Thousands of tiny galaxies. Here's a simulation showing what happens if you drop a cluster in front of them. So here's your backdrop of all these little galaxies. Now I'm going to drop an invisible cluster into the left-hand corner. And you begin to see these mirages that are created, these distortions. And you get the greatest distortion in the centre, where there's this sort of most concentration of mass. You get the most warping of the space, and you get the stronger distortion. And then further out, where the mass gets diluted, you get much weaker distortion. So with this in mind, have a look at this cluster of galaxies. Now, I don't know if you can accurately see them, but you might get a sense of small arcs all the way around. There's a big one here, and altogether it's like looking through, say, the bottom of a tumbler, a glass tumbler, and you get this slight shearing all round the centre of the cluster of galaxies. So, for example, if I zoom in on some of those arcs, you can see giant ones which are right close to the really big galaxies, and then much further out you get finer shearing, and even way out you get just a sense of a general ellipticity of galaxies. And so here is, going back to this cluster I showed you before, you may have noticed this large banana round the large central galaxy. Beautiful case of a giant arc, and where the distortion is greatest, and yet you can see other arcs further out. And again, the cluster that I started my talk with here, enormous arcs. And you see these are blue, usually because they're background galaxies. They could be spiral galaxies. They're nothing to do with the cluster. They just happen to lie along the line of sight. And because there are so many in the backdrop, you get mirages from each of them. So, if you can measure how far away the background source is, how far away the lensing cluster is from you, you can map out all these distortions, and you can work out the mass of the cluster. And not just that, you can work out how the mass of the cluster is distributed. And you find the results agree perfectly with both the motions and the X-ray mass. There is far more mass in the cluster than you actually see in any waveband. And remember, this responds to the total mass that's there, whether or not it happens to be emitting light or not. So within a cluster, again, it varies a lot between different clusters, but for any cluster, you have the mass in galaxies is less than 10%, all the stars and all the galaxies and the gas clouds in the galaxies. The intercluster medium can be somewhere between 5 and 10 times as much mass, but again, that's always less than a quarter of the total mass that's there. You've got up to 3/4 of the, or even more actually, at least 3/4 of a cluster is in the form of dark matter. Stuff that is there, it's got mass, it's got gravity, but it doesn't interact with light at all. Not only does it not emit light, it doesn't absorb light, and it doesn't seem to interact with light or anything except through the force of gravity. And yet it is, a fundamental component not just of individual galaxies, but also on the scale of clusters of galaxies. And what dark matter is a complete enigma. You've really got two choices. Either it's something we understand or it's something it isn't. Okay, that's a little bit trite. But say we understand what we call baryonic matter. We understand electrons, protons, neutrons, stuff like that. Planets, galaxies, stars. There are occasionally ideas invoked that it could be made of ordinary matter. In practice, we can't work out how you can make enough quantities of ordinary matter that don't... You can get stuff that doesn't emit light, like, black holes or compact objects. You can't necessarily get them distributed way out further than the galaxies, and for there to be this huge imbalance of more of that than there is light-emitting matter. We can't make that to make sense. And so most astronomers appeal to the idea of much more exotic forms of dark matter. And again, you've got two choices. You've got one, particles we know about, and it tends to be particles we're talking about rather than large concentrations. Particles we know about, and then particles many of which have just been theorized to actually account for the dark matter. So, for example, in terms of what we know neutrinos exist. So there are so many billions, trillions of neutrinos through space. Imagine they weren't completely massless. Imagine each one had the tiniest bit of mass associated with it. Well, maybe all of that could account for the dark matter. Now, that's a very exciting idea. Doesn't quite match up to the observations, because your problem is that neutrinos are relativistic. They travel at huge speeds. They tend to they kind of resist clumping together. And if you put neutrino-dominated dark matter into models that simulate galaxy growth and structure formation, you find that you get too much structure on too big a scale. It doesn't match what we see. It seems that it's going to have to be one of the other kind of exotic particles that we call them WIMPs, or, weakly interacting massive particles. It doesn't tell you much. It means that weakly interacting, it doesn't actually interact with anything else very much, and it's got a lot of mass attached. And these are things that maybe like photinos or axions or neutralinos. You may have heard some of these names. These tend to be particles that arise out of supersymmetry theories that like to unify gravity with the other forces. And the idea behind this is that maybe these were really important in the early universe. They helped shape our whole universe when gravity was still tied to the other forces. That's why their existence comes out of ideas about supersymmetry and what have you, about this unification. They were really important then, but as the forces disassociated with each other, they are now really fairly slow-moving, they're unreactive to the rest of the universe. In fact, they just sit there and they litter space. So if we can ever work out what the dark matter is, it has profound implications being tied back to the early history of our universe and also the way that matter grows throughout the universe. So, as any astronomer says, we need more data. So you've got strands, obviously the particle physicists are working on detecting necessary particles. Other ways you can look at it, well, you can use all these studies combined on clusters of galaxies under extreme environments. So, for example, when clusters collide. It doesn't happen very often. Clusters are enormous objects, but every so often some are close enough together that their mutual gravity pulls them together and they smash into each other. And when it does, it's one of the most energetic events in the whole universe. Here you have two clusters of galaxies. There's a little one there, little one there. It's a bit difficult to see the distribution of the galaxies. But you can do a lensing analysis, gravitational lensing analysis. You find out where most of the dark matter is, which is colour-coded blue here. And you find the galaxies and the dark matter live in two clumps. Now, these look like they're fairly separate, but in fact, they've already smashed through each other. Because when we look in the X-rays, so this is this hot gas atmosphere that comes from each cluster, you can see it's actually collided and provided a very strange shape. So when clusters of galaxies merge, the galaxies are separated by huge distances. They don't actually have head-on smashes. They tend to pass by each other and just notice each other's gravity and perhaps be slightly slowed down. The X-ray gas, it's pervasive. It fills the cluster. They can't avoid each other. The two intercluster media slamming into each other, squeeze each other, compress each other, and slow each other down. In particular, you can see that the smaller cluster, it's kind of got this bullet shape. This is known as the bullet cluster. There's been like a drag force, similar to air resistance, that's slowed down the intercluster medium. And you find that the intercluster medium has got dragged out and stuck in the middle. And the curious thing is the dark matters behave like the galaxies. It's just sailed past each other, only notice the gravity of the other. There's none of this kind of interaction that you see with the X-ray intercluster media. So here's a simulation indeed. Dark matter in blue, X-ray gas in pink, small cluster going through, big cluster. The dark matter sails through, unaffected. The X-ray intercluster medium severely distorted, compressed and squeezed by the interaction to produce those structures that we see. And so this is a way of modelling how dark matter behaves, how it interacts on huge scales. And there are only a handful of these galaxies studied, but they all but one, all seem to show this kind of behaviour. So we're beginning to map out how dark matter reacts to other matter on enormous scales and how the distribution might vary. A handful of these discovered, nearly all behave like this, apart from this one, released last week. You've got one cluster of galaxies here, another one here. I'll just code the galaxy distribution in orange. If you look at the dark matter distribution from the lensing, it's actually separated out. And in fact, it seems to lie where the intercluster gas is in the X-rays. And again, you can see some compression structures within the intercluster gas. And so here, this is a very strange one that bucks everything else we've seen in mishmashes of, cluster collisions. It could be that this is just an oddball. Maybe it's a three-way collision of clusters of galaxies or something. Or maybe this is something profound to tell us about dark matter, the fact that it's actually lagged behind the galaxies. It seems to be behaving more about the gas. So this is, again, this is stuff that's being done over these few years. It's relatively recent discoveries. And hopefully more detailed analysis of the distribution of dark matter and the relative components of the cluster may start to tell us more about it. But as yet, it's still a huge unknown. So finally, this brings me to the idea that if galaxies are close enough to collide with each other from time to time, you get the sense things are still evolving, things are still changing, and clusters of galaxies are building up to form superclusters. If I go back to the all-sky distribution of structure, you can see these knots and concentrations of galaxies, and this has got some depth attached in that blue to red, you're going further out away from us. You can see that these knots join up and link up to form sort of linear structures that we call walls or slabs, and these are superclusters. I told you about the Shapley supercluster that was discovered in the 1920s by Harlow Shapley. That is our nearest big concentration in the sky. Now, so here's some three-dimensional maps from Richard Powell, beautiful demonstrations of the local geography of our universe. You are down there. You can probably barely see where it says Milky Way. You're down in this corner. This is the Virgo cluster, our nearest rich cluster, and you'll see the local group is kind of like hanger-on to the Virgo cluster. And there's a link in each of these yellow things. Each of these names marks an Abel cluster. There's a smattering of galaxies along a line, and this is a true line in three-dimensional space. And over here, you've got something like 30 Abel clusters. 6 of those are amongst the brightest 46 known in the universe. And they all sit within a volume of perhaps a few tens, probably up to a couple of 100 million light years across. If you look at the dimension of this supercluster, you've got 30 clusters in that size, and down here you've got like the Virgo cluster in the same space. This is truly a supercluster, and you find they are endemic through the universe. Again, just going back to perhaps this first bit and giving you much more of a three-dimensional distribution of galaxies. You are now here at the centre, local group tagging onto the Virgo supercluster, and you begin to get chains of clusters joining up, and then knots where the filaments and the chains intersect to form superclusters. And panning out a bit, there's your Shapley supercluster and that chain of galaxies. Perseus Pisces over here with the Perseus cluster. You get a wonderful idea as we move further out with redshift surveys, the distribution of clusters and galaxies on the sky, that these clusters are linked up and in long chains of superclusters, and superclusters where these chains and filaments intersect, and they surround enormous voids of space where there's barely any galaxies. So you have sort of voids like Booty's void, Capricornus void, where there's barely any galaxies. And on huge scales, the universe has this cellular or kind of cobwebby structure about it. So as you move out, it's not like you get bigger and bigger clusters or anything. You just get this repeating cellular structure within the universe. And this is the large-scale distribution of galaxies. The first thing it tells us is that superclusters are still forming. Galaxies are nice and stable. They've kind of sorted out where they are, or the galaxies know where each other are. Superclusters, clusters are still merging to form supercluster structures. They're still evolving. So even though they're the largest structures in the universe, they're not truly done, gravitationally bound, stable entities. They're changing and they're evolving. And these structures, this sort of linearity, starts to tell us something perhaps about how structure formation grows in the universe. So, for example, one thing that I always find very intriguing about clusters is there's an alignment right from the largest scale right down to the central cluster galaxy. I could show you any number of examples. I'm just going to pick, well, here is some, for example, where you have these contours are of the X-ray emission. So that's the shape of the puddle of X-ray gas. That's the shape of the cluster. And I've kind of given you an alignment by eye on that. And these are contours of the brightest cluster galaxy, same clusters up and down. And you can see that they share the alignment. If I want to go into detail, for example, with the Coma cluster, here's one of those giant ellipticals, and that's my rough axis about how, perhaps it's kind of a bit more like that, but how it's aligned. That then, with its neighbouring galaxy, lie along that axis. If we span out a bit further and look at the distribution of all the galaxies in the sky, perhaps it's tilted around a bit, maybe the axis is a bit more like that, but it's still along the same sense. Moving then further out to the X-ray emission that I showed you earlier, again has a slight elongation this way. This subcluster here is merging in from that direction. And then if we map out all the neighbouring clusters of galaxies, you'll find the local superstructure is aligned along that way. And these are true alignments in three-dimensional space if you start putting depth into it. And so there's something shared about the alignment of the supercluster right down to the central cluster galaxy. In a sense, this is some echo, perhaps, of how the clusters form. And this gives us a constraint for cosmological theories that want to simulate the formation of clusters of galaxies, the growth of structure right from the early universe to the present day. Can they reproduce clustering on the right scales? Can they reproduce these voids? It is a huge challenge. It assumes you know something about the dark matter distribution, the visible matter distribution, how clusters collide. There's an enormous amount of physics that goes into it. And there is this complete industry of producing cosmological simulations where you vary the cosmology. Do you get out this large-scale distribution that you see? And here are just some steps in time. So at the bottom here, you have time since the beginning of the universe. So that says 200 million years. And these are just snapshots from a fabulous simulation called the Millennium Simulation by Volker Springel et al. And these are different scales: large scale, middle scale, very small scale. And as we go forward in time, you can see that things start to congregate along these filamentary structures. And in fact, we think that matter flows in and galaxies and clusters merge along preferential directions along these filamentary structures, and that preserves the alignment both of the supercluster and the galaxy and the cluster, and then right down to the galaxy. There's this coherent sense that matter accumulates again along the filaments, and you grow large clusters of galaxies right down there deep in the core. And this is one of the ways in which clusters of galaxies can provide very powerful cosmological constraints. It's not the only way, of course. I've talked a lot about the contents of the clusters and the properties of the clusters. I don't have time to go into other ways that we can use clusters as constraints for cosmological theory. You can have a talk on that next year, okay? Clusters are everywhere in the universe. They provide very important constraints for the whole idea of the whole flow of the universe and its expansion. But that's a completely different area of cosmology, but I will be revisiting that next year. But nonetheless, I hope you can see that even just like within the cluster itself, the dynamics of the galaxies, and also the linking of clusters and the large-scale structure, we've still an awful lot to learn, just both from the contents and also about the much wider universe. And I think these are really important structures to study. So that's enough about clusters of galaxies. For those of you who might be interested, I'll just put a quick flyer for my next talk. So I'll be coming back in May. And as I keep saying, everybody wants bigger telescopes and more data. Well, that's part of the reason, but I'll talk about some of the challenges about building the very large telescopes we need to carry out these kinds of observations. Thank you very much.
You just mentioned dark matter before you were talking about dark energy on the edges. Are they one and the same thing?
No. So dark matter is mass, and it has gravity, and it is, so it's associated with, a pulling force. Dark energy is associated with an absence of stuff, an absence of mass, and it's a pushing force. And indeed, that's what I'm alluding to when you map the distribution of clusters and galaxies and their recessions from us. That's where the evidence for dark energy comes in. So if you like, extending this idea of galaxies as the thing we're most used to talking about, galaxies is just like n% of a cluster, dark matter is somewhere between 70 and 90% of a cluster. If you then start averaging out the whole universe, so voids and clusters and superclusters, you will find all of that, everything I've mentioned in today's talk, so the matter that's giving off light, the matter that's dark, that's less than a quarter of the whole universe in terms of mass energy density of the whole universe. And so actually the dominant component of the universe is dark energy, and we know even less about that than we do about dark matter. Which is really exciting, by the way. That's a good thing.
I find it quite amazing when you have the collision of the superstructures that one can pass through another.
Yeah.
Is it the dark energy that causes that to happen? Or, what is it that gives a difference between the two? They don't coalesce. One goes right through.
Again, it's gravity on the scales. The thing that's gravity is the pulling force. That's what's pulling those two clusters together. And the thing is that in terms of the individual galaxies, they don't, there's so much space between the galaxies. Separation between the galaxies is much bigger than the size of a galaxy. So they don't head-on smash. They tend to go past each other, maybe notice the gravity of the other galaxies. It depends how fast they're moving. If they're moving really slowly, then they'll slow down and notice the gravity. And probably what happens is that you have to have several passes through before something actually merges. So sometimes in the X-ray gas we see things we call sloshing, or like ripples, where something's gone through and back and then it kind of settles, and we see the after effects of a merger. Something like the coma cluster, for example, with the fact you've got those two giant ellipticals suggests that it's a merger. A long time ago, there was a merger of two fairly equal clusters of galaxies together to produce that. Each had their own brightest cluster galaxy coming together. So it's gravity that's driving the interaction, and it will eventually cause them to merge. If the small cluster's going too fast, then maybe it'll go on. But if it's going relatively slowly, it'll go so far and then get pulled back together, and so you'll oscillate and then they'll collide like that. But the time, actually finding them at that moment where they're kind of passing through each other, and that first pass is quite rare. It's quite a short, it's only a few 100 million years for that, for that to see. So that's why it's quite rare to actually catch them in the act of merging. We tend to see clusters that may be sort of bimodal or something, suggesting they're the remnants of a merger.
Dark matter again, I'm afraid. One wonders how much baryonic matter we're missing. I'm thinking in terms of objects being obscured by other objects, and indeed the lensing effect, where we're inside the focus. There must be other situations as well. Has that ever been calculated, how much potential there is in that?
Yes, in fact, some people very specifically target areas where there isn't a visible cluster of galaxies in the way, and they just look at that background field, backdrop of galaxies, and look for tiny shears that suggest there could be concentrations of dark matter that are not associated with galaxies or clusters along the way. And it's very hard science to do, and yet there's no evidence for large clumps of dark matter that are not, associated in some way around the periphery of clusters of galaxies. Also, say on small scales between us and Andromeda, the idea there could be small dark objects along the way. It could cause what we call microlensing, sort of one-off events if they pass between us and a star and the alignment is right. Again, I'd say the evidence for that is very inconclusive, and we're certainly not finding baryonic matter in the quantities we need to account for the dark matter that's needed on these scales. So, it could be there's some great observation yet to come, but at the minute, the best guess is it's something much more exotic. Okay, thank you very much.
For all information, please visit www.gresham.ac.uk.